In this video, we're going to be learning how to draw ray diagrams for concave mirrors and describing images that form in concave mirrors with those ray diagrams. We'll also see some applications of concave mirrors. As a reminder, there are two types of mirrors we're studying in this course. We've seen plane mirrors, and now we're moving on to curved mirrors. The curved mirrors can be concave, which curves inwards, or convex, which curves outwards. In this video, we're going to focus on the concave mirrors. In the following video, we'll focus on convex mirrors. Let's start going over some terminology first before we go into the actual ray diagrams. You can think of a concave mirror or even a convex mirror as a mirror that's cut from a sphere. So here's a ball, and you cut a piece of the ball out, and there's a part that curves inwards that's on the inside and a part that curves outwards. We're studying the part that curves inwards, the inside surface of this ball. So this is our concave mirror here. We often call concave mirrors converging mirrors. So to converge means to meet at a point. So you can see here all these light rays that are parallel to each other. When they hit the mirror, they all reflect and reflect onto this point here, and that's called the focal point. But the point is that concave mirrors are called converging because they bring light rays closer together. They make light rays meet at a point. So let's go over some more terminology here. So this is our concave mirror, also here. You can draw what's called a principal axis. The principal axis is a line that cuts the mirror in two. It's drawn right through the center of that mirror. The vertex is where the mirror meets the principal axis. So right here, represented as V. Principal axis is often labeled as P or PA. The focal point, you can draw it on your principal axis here. That's the area where parallel light rays would hit the mirror and then meet. So you could find a focal point of a mirror by basically putting a bunch of parallel light rays together here, making them hit the mirror and seeing where they meet, and that would be your focal point, represented by the letter F. The center of curvature, big C or 2F, is simply 2 times the distance of the focal point. So let's say the focal point was 5 centimeters away. Well, the center of curvature is 10 centimeters away. The radius of curvature and the focal length are measurements. So the focal point is a point, the center curvature is a point. But when you're measuring how far they are from the mirror, we give those different terms. So the radius of curvature, R, is the measurement from the vertex to the center of curvature. That's called the radius of curvature. And the focal length, little f, is the measurement from the vertex to the focal point. So we have the focal length and the radius of curvature. And these are important points because when we discuss image formation in concave mirrors, we're going to describe where the images are compared or relative to the focal point and the center of curvature, or 2f. So this is a brief introduction to some of the terminology that we're going to use for concave mirrors. And a lot of these terms will be applicable to convex mirrors as well, so it's important to really grasp these concepts now. When we're describing images for concave mirrors, we're going to use the same tricks we used before, lost or salt. And what I want you to get is that as we go through the example, there's going to be a variety of different cases we're going to see. So in plane mirrors, the image was always upright, HIHO, DI is equal to DO, and virtual. It didn't matter where the object was in front of the mirror. It was always kind of the same sort of characteristics compared to the object. For concave mirrors, the image characteristics are dependent on or will be different depending on where your object is placed. If your object is over here, between the focal point and the mirror, that'll give you a certain set of image characteristics. If the object is on the focal point, if the object is at the center of curvature, if the object is in between the center of curvature and the focal point, that'll give you different image characteristics. If the object is beyond C, beyond 2F, farther away than the center of curvature, that'll give you another set of image characteristics. So what we're going to do is we're going to go through a series of examples that shows us the image characteristics for these 5 different cases. Now, you can memorize these cases. I'd recommend you start off by drawing ray diagrams to discover the cases, and then you sort of memorize them as you do more practice. It's important for you to know what the image characteristics are, though, so you can answer questions pretty quickly on assessments or when you're thinking about concepts to try to solve problems. So, these are the main steps that we're going to use to drawing ray diagrams for concave mirrors. The nice thing about concave mirrors is we're not really going to have to use a protractor. The law of reflection still applies, but it's not as easy to use a protractor to identify the law of reflection because the mirror is curved. It's not a flat surface. So instead what we do is we memorize certain rays that we use to draw our images. So the first ray is one that goes parallel to the principal axis. When that hits the mirror, it reflects through the focal point. And it does follow the law of reflection. The normal would actually be right here. It would be a dotted line that goes through the center of curvature. And if you measured the angle there and there, they'd be the same. But we don't have to draw the normal for this. You can just memorize parallel through the focal point. The other ray you can use is one that goes through the focal point. As the incident ray goes through the focal point and hits the mirror, it's going to reflect parallel to the principal axis. So it's almost like it is the opposite of this one. This one is parallel through focal, this one is through focal, parallel. You could use a ray that goes through the center of curvature and then it bounces back on itself. And so think for a minute about what that means about a line that goes through the center of curvature. If you guess that that means that the normal goes through the center of curvature, then you're correct. Plus, I said it over here anyways when I was talking earlier. So it's important to pay attention to some of those details and to think about previous terminology as well. Another ray you could use is one that hits the vertex and then reflects. Now this one here, the only thing with this one is that you're going to have to measure the angle here and here, because if this is 25, then this has to be 25. So there's no clear direction as to where to go. So you could do the vertex and then it reflects, but you have to measure those angles in that case. That's why I prefer to use these three rays when I do these ray diagrams, because I don't have to use a protractor at all. But you can always use this to check your work if you'd like. So these are the special rays that you should be memorizing so that you don't have to use a protractor when you're doing ray diagrams for concave mirrors. So in this video, we saw special rays to memorize. We saw terminology for concave mirrors. In the next video, we're going to see the different cases for objects in front of concave mirrors and what the image characteristics are going to be based on those cases. And we'll discover those as we do ray diagram practice.